everybody. In this video, we're going to talk about how to simplify radical expressions. Okay, so in this video, we're going to focus on square root and cube root. So that's when the index of our radical is a 2 for square root or a 3 for cube root. And these principles or these rules that we're going to look at today, they extend beyond cube root to the fourth root, fifth root, so on and so forth. Okay, so first of all, what is a radical expression? Well, a radical expression is just an expression that contains a radical. Okay, so what is a radical? It's that square root symbol that we see, and that's oftentimes what we call it, is the square root symbol. Okay, so in order for us to simplify radical expressions, there's three things that we need to make sure of to make sure our radical is in simplest form. Number one, no radicands. What's radicand? That's the number under the radical, where I have that green box, have perfect nth powers as factors other than 1. So what that's saying is if we're trying to take the square root, we just want to make sure we don't have any perfect squares as our radicand, right? So if I have the square root of 36, I want to simplify that to just 6 and so on, okay? No radicands contain fractions. So if we have a radicand that's a fraction, we can split up our radical and take the root of the top and the root of the bottom, or the square root of the numerator and the square root of the denominator. We'll take a look at an example like that. And lastly, no radicals appear in the denominator of a fraction. So in this video, we might not see those right off the bat, or we're going to see maybe a couple, but they simplify really easy because it's a perfect square or a perfect cube. And then in a separate video, we're going to talk about, okay, what happens if we do have a radical in the denominator? And that's called rationalizing the denominator. So the card for that video is at the top right-hand corner right now. So let's get into simplifying some radical expressions. And let's start with square root examples. So the first one that we're going to look at is the square root of 147 for number 1. Number 2, we have the square root of 25x to the 5th. Number 3, the square root of 13 over 49. And number 4, the square root of 196 over x to the 4th. Okay, so what we're going to do is we're going to think about, do we have any perfect square factors that can be divided by 147, or that are factors of 147? So if we play around with it a little bit, we know it ends in a 7, so we can think about some multiples of 7. And actually 49 is a factor of 147. Okay, so if we do, let's say the square root of 49 times the square root of 3. So if we check that and we do 49 times 3, then that's going to give us 147. So what we are able to do here is kind of separate our radicand, 147, into two factors. And the goal of that is to give us a perfect square factor so that we can simplify it. And we've gotten a perfect square factor with the square root of 49. So now we could write this as the square root of 49 times the square root of 3. And the square root of 49 is 7. So our final answer would just be 7 root 3, or 7 times the square root of 3, okay? All right, number 2, now we have a variable in there. So let's kind of take it step by step. Let's separate it just like we did on number 1. So let's say the square root of 25 times x to the 5th. And now let's separate those. So let's do the square root of 25 times the square root of x to the 5th. Okay, square root of 25, that's a perfect square. That's going to give me 5. And now I can think about some of my exponent rules, linked to that video in the top right-hand corner right now, in order for us to simplify x to the 5th. So let's take this and let's think about what exponent is going to cancel out with a square root sign. Well, that's an exponent of a 2, right? If I square a number and then I square root it, those are called inverses. So if I can write x to the 5th as x squared times x squared times x to the 1st, that's still equal to x to the 5th, because this is like what I call the MADS property. It's a multiplication problem. We're adding, so we can add the exponents. So if we add those exponents, 2 plus 2 plus 1, it's still x to the 5th. So what this allowed us to do, we still have this 5, but now we have times the square root of x squared times the square root of x squared times the square root of x to the 1st, or just the square root of x. So now those two square root of x squares, those are going to cancel out and just give me x. So we have 5 times x times x times the square root of x. And now we can simplify to get our final answer. So we get 5x to the x squared times the square root of x. And that would be our most simplified answer for number 2. Okay, so now for 3 and 4, we have some fractions. So just like we've separated the multiplication into two separate radical expressions, we're going to do the same thing with a fraction. So I'm going to start off by saying this is the square root of 13 divided by the square root of 49. We've already seen the square root of 49. We know that's equal to 7. So we can just simplify this to the square root of 13 over 7. Okay, and there's nothing else we could do with 13. It doesn't have any perfect square factors other than 1, and so we can leave that just like that. It's okay that the radical's in the numerator, we just don't want it in the denominator. Okay, last one for square roots. Simplify this, we're going to break it down, square root of 196 over the square root of x to the 4th. 196 is a perfect square, that's going to give me 14. And the square root of x to the 4th, we could break that apart just like we did. We can say x squared times x squared. And that's essentially exactly what we did right here. So we know that that is going to cancel out those exponents of a 2 with that square root sign. So we could say this is 14 divided by the square root of x squared times the square root of x squared, which is going to give us a final answer of 14 over x squared, right? Because that'd be 14 divided by x times x, and x times x is x squared. All right, now we're going to take a look at some cube root examples. So for cube root, we want to think about not perfect square factors, but perfect cube factors. So our perfect cubes, we've got 1, we got 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 125, so on and so forth. So our first one we're going to do is the cube root of negative 135, and it's okay for us to have a negative radicand because we have 3 factors here, right? Cube root would be what number multiplied by itself 3 times gives me this negative 135, so it's okay for us to have negative. So let's think about some factors, and I can think that 27 is a factor of 135. So I can separate this into the cube root of negative 27 and times 5 would get me to negative 135. So now let's separate that into the cube root of negative 27 times the cube root of 5. So now the cube root of negative 27 would be negative 3 because negative 3 times negative 3 times negative 3 would be negative 27. So we have negative 3 cube root of 5 as our final answer, okay? All right, for number 2, we have the cube root of 512 x to the 5th. So we can separate this cube root of 512 times the cube root of x to the 5th. Cube root of 512, that's a perfect cube. That is 8 cubed. So this is equal to 8. And now let's separate this. And now instead of us trying to find x to the 2nd power to cancel, we need x to the 3rd power. That will cancel with a cube root. So let's write this as x cubed times x squared because we would add those exponents, 3 plus 2, still x to the 5th. So now we have 8 times the cube root of x cubed times the cube root of x squared. And the cube root of x cubed, that's going to cancel out. So we have 8x, and we can do the cube root of x squared. And that'll be our final answer for number 2. For number 3, we have a fraction, so we can separate this. Let's do the cube root of x squared in the numerator and the cube root of negative 729 in the denominator. Well, in the numerator, we see exactly what we just saw on number 2, and there's nothing else we can do with that. We can't simplify that any further, and it's okay because that radical is in the numerator. So let's take a look, cube root of negative 729. 729 is also a perfect cube. It is 9 cubed. So all we have to do is simplify our denominator to negative 9. And the last one, number 4. Let's separate this. We're going to say the cube root of 343 x to the 7th divided by the cube root of y cubed. Once again, we have in the numerator a product, 343 x to the 7th. So we could say the cube root of 343 times the cube root of x to the 7th, and then over the cube root of y cubed. Okay, so now the cube root of 343, also a perfect cube, that is 7 cubed. So we can write this as 7 times the cube root of, and now let's separate x to the 7th to get factors of x cubed, because that's what's going to cancel, right? So x cubed times x cubed times x divided by, and then in the denominator, that's just going to cancel out to give us y, okay? And so now we have 2 cube root of x cubes here, so those are going to be able to cancel. So our final answer, we're going to say 7x squared cube root of x all divided by y. Okay, and that is how you simplify radical expressions with cube roots and square roots.